which is DSTF sponsored, Shishadra College of Web and Salem. At the outset, I want to indicate that I am very much pleased and honored to be invited as a session chair in this important webinar. We hope that start the plenary session in this introduce to Sandeep Mayura, who need no introduction in this field, but officially we should have some basic what to tell. We should intro him officially. Yeah, Dr. Sandeep Mayura, who serves as a research scientist under the Division of Materials Synthesis Integrated Devices Group, Los Alamos Laboratory, New Mexico, USA. Today, he hopefully covers a topic entitled Electrochemistry for Sustainable Energy in Future. A small introduction about his education qualifications and the vast experience he has in the research. Dr. Sandeep Verma, who completed his BSc in Veer Narmad, South Gujarat University, completed his PG, the MSc in Maharaja Sayojirao University of Baroda, and pursued his PhD from Gwangju Institute of Science and Technology, South Korea. He has a very vast research in various fields like material science, electrochemistry, polymer for fuel cells, redox flow batteries, and goes on. He has a multi-talented researcher. His thrust area is membranes and separated technologies, which include casting, coating, spinning, modification of membranes. So his credit has around 2 patents and more than 50 research publications, high impact journals like RSC Advances, Electrochemistry, goes on, moves on. Dr. Sandeep Verma has completed 2 major research projects, and other projects are going on, hopefully successfully. Further, Dr. Sandeep has total citation of about 1300 and H index of 21, and similarly I index of 31. Professor Sandeep has participated in various international conferences and presented in both oral and poster way. He serves as a reviewer in well-established journals like RNC Advances, Journal of Material Science, Macromolecular Materials Engineering, Material Chemistry and Physics, Electrochemistry and Communication, and this too has a long list to his path. Professors, Dr. Sandeep has attached himself in various recognized professional memberships like National Postdoc Associations, Electrochemical Society. Further. With this small introduction, I request Dr. Sandeep to present this lecture, sir. Thank you for a great opportunity to offered by Indian Chemical Society Tamil Nadu branch and Shishadra College of Women, Salem. With this few words, I welcome Dr. Sandeep, sir. Please take your dais, sir.
Thank you very much for your kind, introduction. Can you hear me really well, or is there any issue with my voice?
Okay, sir. Your voice is fine, sir. Could you please share the screen?
Yeah. So now my voice is fine. So let me share my screen. Okay, can you see the first slide on my presentation?
Yes, we can see. Please go ahead, Professor.
Okay, so first of all, I would like to thank you everyone for inviting me here, and a special thanks to Dr. Akila Nandeshwari and Dr. Sukumar for making it possible today, because Dr. Kannan, who was supposed to give the lecture before me, he had some medical emergency and has to travel to India right away. So Dr. Akila and Dr. Sukumar reached out to me, and they made it possible in very short time. So I would like to give them special thanks. And also, I'm very thankful to Sri Sharda College for Women, as well as the Indian Chemical Society for this webinar series. And with this introduction, let me start with my presentation. So today I am going to give my talk on electrochemistry for a sustainable energy future. So Dr. Umarani has already gave us like a really nice introduction why we need sustainable energy future, because there are like billions of people who don't have regular like they don't get electricity on regular basis. So because of that, sooner or later we need our like energy future to be sustainable. And given that all our energy needs are today comes from the petroleum, it might not be possible in future when petroleums are depleted. So let me give you my short introduction. My name is Sandeep Maurya, and I'm currently a staff scientist in Los Alamos National Laboratory. And with that, I would introduce a little bit about Los Alamos National Laboratory. So Los Alamos National Laboratory is a part of a cluster national laboratories in US, where there are like more than 15 to 16 national universities, where Los Alamos National Laboratory is one of them. So this is something like CSIR labs in India. So all these labs are actually supported by Department of Energy, and typically this Los Alamos National Laboratory is supported by Nuclear Administration of Department of Energy. So this lab only started up like during the World War II, where the primary goal for this national lab was to help with the development of atomic bomb. But with time, Los Alamos National Lab has been established in other research also. So let me give you a little bit of statistics about Los Alamos National Lab. So the lab itself is like spreaded in 40 square miles of area, and it has a total of 1,280 buildings, which has 19 million square footage. And there will be 13,000 people working all the time in the laboratory, and there are like 8,900 full-time employees and 1,100 students, and there are roughly 500 postdocs all the time associated with Los Alamos National Lab. And as you can see, let me turn on. As you can see here, the financial year 21, Los Alamos National Lab has a budget of $3.7 billion. And as you see, like other than the 73% which is related to weapons, other fundings were for energy applications or for energy research. And here is the nice photo how Los Alamos National Lab looks like from the far away. Okay, so in the past, as I said, like in 1940s, lab was mostly involved in development of nuclear devices. And here you can see like this is the like small model for the little boy. And today, with the time, lab has evolved, and now lab also focuses on national security issues such as energy security as well as the global security. And in energy security, we mostly focus on materials as well as climate energy nexus, apart from nuclear energy. So Los Alamos National Lab has prioritized all the investment across like in 4 different categories. And those categories are materials for future, science of signatures, complex natural engineered system, integrated for prediction. So these all things are like they are either like associated with energy or they are associated with the national security. And most of the time they are associated with the energy security in the United States. So my work, which is on mostly fuel cell, actually fits really well with the materials for the future, where we are developing the fuel cell technology to solve the energy issues of the future. So this was the history of Los Alamos National Laboratory, but let me give you a little more history about how fuel cell program, little bit of fuel cell program in Los Alamos National Lab. So this is as you might know, that the fuel cell were used in NASA satellite programs. However, though this technology was considered very expensive and has very little uses in practical applications. So scientists at Los Alamos National Lab, they started researching fuel cells for transportation program in 1977, and they made very key discoveries in this field, and because of that, this program has now grown into a different office in the Department of Energy, which we call as Fuel Cell Technology Office. And so major problem with NASA's fuel cell technology was it was using platinum catalyst, which is very expensive. And because of that, the cost of a fuel cell system is pretty high. And if the cost is high, then the applications such as, let's say, the car, fuel cell car, or stationary power applications, they will be expensive, and the energy price per kilowatt will be much higher than conventional sources, and which is the kind of roadblock. Give me a second.
Can you hear me? Hello?
Yes, sir. Yes, sir. Please go ahead.
Okay, so I think my headphone stopped working. So let me start again. So most of the roadblock comes from the cost of the system. So okay. Okay, so yeah, so as you can see here, the one of the key development was made at Los Alamos National Lab was to introduction of ionomer, which we call as here the polymer chains. What you can see here, we call it as ionomer, and if you mix with the ionomer with the platinum support carbon supported platinum particles here, so this will reduce the platinum content in the fuel cell system drastically, and that will help to achieve cost targets of fuel cell system. So based on this technology, in 1970s, we have developed some transport applications for with the fuel cell. Okay, and here is our fuel cell team. So we have around 20 scientists and a lot of postdocs. So if you combine all this experience of these people, then it goes over 200 years of expertise in fuel cell. So this is how extensive fuel cell program is at Los Alamos National Lab. So now let me show you a little bit of about electrochemical application, real world application. So let me start with the batteries here. So as you can see here, this is the one schematic of how lithium-ion batteries work. So during the charge and discharge, there will be lithium-ion transporting from anode to cathode, vice versa. And this is the if you look at lithium-ion batteries, these are all based on the electrochemistry, and let's say if you go before 20 years ago, you wouldn't find a lot of mobile devices, but if you look at today, almost every electronic device is mobile because of the high energy density lithium-ion batteries are available today. So so this is kind of lithium-ion batteries are responsible for mobile revolution. And batteries were known to humans for like 2000 years. And one of the example is the Baghdad battery. And it used to like people were using these batteries to electroplate metals with gold or other precious metals. So this is one of the noticeable example of electrochemical application. And if I'm considering the second, then that is fuel cell. And it was first invented in 1939 and only used by NASA in 1960s in Gemini program and other satellite programs. And if you look at how the fuel cell has evolved, so after 1970s, there were like a lot of interest in fuel cell, and General Motors started building cars with fuel cell. However, it didn't go well because of the higher cost. And during 1980s, the gasoline prices were dropped a lot, and because of that, it wasn't economically like attractive to build a fuel cell car, where like if you're gonna spend a lot of money to fuel the hydrogen in your car and gasoline is much cheaper than that, then people would prefer gasoline based car. So this is the second application. And there are other applications, but these are like major applications which I think most of the people have heard. So one of them is, let's say, supercapacitor. So supercapacitor is in general, the capacitor could not provide higher energy for longer time. It can only provide for short time. But then there are supercapacitor, and then there are hybrid supercapacitors, where scientists, researchers are making breakthroughs so that they can be used as a battery, like a high energy and longer time and energy source. And there are a lot of industrial processes. One of them is, let's say, chloralkali industry. So in this, what they do is they have this Nafion membrane in their reactor, and they have these two electrodes where they can provide current. And based on that, what you will see is NaCl. From NaCl, you can produce chlorine gas, hydrogen, as well as sodium hydroxide. And as you know, sodium hydroxide is very important industrial material, which is used in several applications. So overall, electrochemistry is a kind of it's being used in a lot of things, but we don't pay that much attention. But I think electrochemistry is kind of involved in almost everything, in all major applications in industry today. And so we during the introduction, I said hydrogen is important, and also we need if we need sustainable energy future, then it can be attained by many ways. But one of them is to generating the hydrogen and making every process hydrogen based, so that can actually provide us a sustainable energy future. For example, let's say if you have a hydrogen, you can use that hydrogen directly in transport application. You might have heard about fuel cell trains also. And nowadays people are even trying to use hydrogen in cruise and all those sea route transportation. And there are applications. If you do the CO2 reduction and combine with the hydrogen, you can actually synthesize ethane, methane, or ethanol, those kind of molecules which can actually used later as a fuel. And same thing, we can actually upgrade to the biomass, or this ammonia fertilizer is a pretty hard reaction. Right now people are using Haber-Bosch process, which is energy dense. However, electrochemical process can be better, but we are still electrochemistry field is still waiting for the breakthroughs. And the same thing, we can use the hydrogen for chemical and industrial process, or to for the heat. So we now we have the hydrogen. However, but how we can produce the hydrogen? So in order to produce the hydrogen, we need support from the electrical grid. So hydrogen itself can produce, can supply the electricity, but we need renewable energy sources to in our grid, so that whenever we don't need, like we have excess of energy, we can produce the hydrogen, which can be later used for this application, or which can be used to produce energy. So right now we have like most of the energy comes from the conventional sources such as hydro and fossil fuel. But if we replace those with the renewables and nuclear, then the hydrogen dream can be achieved. So overall, if the hydrogen has potential of $140 billion in US, which can create 700,000 jobs and reduce the greenhouse gas emission by 16%. And the good thing is, with the always development in the technology, cost for hydrogen is hydrogen is becoming much cheaper and cheaper every day. So I am hopeful that one day we might adopt like hydrogen economy in our day-to-day life. So I have talked about like this hydrogen economy and all this stuff. However, how this hydrogen actually how hydrogen works to generate the electricity. So I can show you the example of a proton exchange membrane fuel cell, where this is the proton exchange membrane, which only supports the transport of proton. So when you supply the hydrogen on one side, then there is an anode where the platinum catalyst along with the anode, which this is the structure I showed you. So here is the anode and here is the cathode, and this is your proton exchange membrane. So now hydrogen enters here, it gets absorbed on the hydrogen and becomes hydrogen plus and generates one electron here. And then this hydrogen plus ion transported through these ionomers and reaches to the membrane. And now because of the proton gradient on this side, and there is no proton here, this proton will move on to cathode. And here, where the oxygen is already absorbed on the platinum surface, an electron came from the outside of circuit, reaches here, and then H plus and adsorb oxygen, they form together water molecule and produce water. And by doing this, this electron will travel through the circuit. So this is how it generates the electrical energy. And then there is another type of anion exchange membrane fuel cell, which uses the anion exchange membrane, where this oxygen along with water molecule form hydroxide ion here. And because the hydroxide ions are higher in higher concentration here, it will transport it through the anode where there is a hydrogen present, will react with that and form water. So benefit of this anion exchange membrane fuel cell is that because of the alkaline environment, it doesn't require precious metal catalysts such as platinum. So if we can make several breakthroughs in anion exchange membrane fuel cell, then we can actually use a non-precious metal catalyst in like in fuel cells. So here is the structure of how the interface looks like, and I have already explained like how the electrochemical reaction takes place. And so here is the kind of schematic of a fuel cell car. So fuel cell cars have actually very little part, like mechanical parts, and because of that, they can be a better choice for transportation. However, because hydrogen is not easily available, this technology has a roadblock right now. So far, I have shown you like electrochemistry for hydrogen and fuel cells. So electrochemistry is also involved if you want to reduce the like CO2. So with this one, what can happen is like now, so far what we have done is we have produced the energy. But if you want to remove the total uses of petroleum, like up to zero, then how we gonna, like in today's world, whatever clothes we wear, whatever furniture we have, everything is little bit or up to like 100%, it is associated with the petroleum, such as like our cloth, polyester comes from the petroleum. So let's say if in the future, when we don't want to use the petroleum at all, how are we gonna produce these chemicals? So because of that, so CO2 reduction is nowadays very like gaining attention, and CO2 reduction has the capability of reducing the CO2 from the environment, as well as producing the feedstock material for value-added chemicals such as methane, ethane, ethanol, and this can be further used for synthesizing other chemicals. So this is one example of CO2 reduction reaction, and here this is another example where we don't need to use the alkaline membrane. Instead of that, we can use bipolar membrane and produce the CO2 based chemicals. Most recently, this paper, what they have done is they started from CO2, and with several processes they were able to synthesize starch, which is the food. So if we like if the development goes on, then one day, who knows, our food might be synthesized from the environment, like environmental CO2. So far what we have done is, like, we have covered the energy, we have covered the chemicals, and what happens when we have the excess energy. So in order to save that, either we can produce the hydrogen, or we can save that energy in redox flow batteries, where we can charge these redox flow batteries here, and then the electrolyte, which is charged already, we can refill in this electrolyte tanks, and that way, whenever we need energy, we can pump this electrolyte back to the cell and produce the energy. So there are several technologies such as zinc bromine, polysulfide bromide, iron chrome, all vanadium, and they have some advantages and disadvantages. However, this technology, all vanadium, has been commercialized. As you can see here, these are the tanks of vanadium electrolyte, and these, as you can see here, and they can harbor more than like a megawatt of energy. So whenever, let's say, if in future, if we abolish coal 100%, then how are we going to get energy when there is no sun or there is no wind? So during that time, these batteries can kick in and provide energy what we need for our daily life. So far I have covered like background for energy, background for chemicals, and background for batteries. So like once we combine all in one place, then only we can dream for a sustainable energy future. So this was all about the background, but now I will go to the little boring section where I will talk about some of my research. And so in my today's talk, I will talk about this is going to be in two parts. One is related with the fuel cell, another one is about flow batteries. So sorry. It's not me who is
Jolly. And not played in a time of the
can someone remove this from the screen? Thank you. So in this part one, I will talk about effect of phenyl adsorption. So if you remember the figure where the catalyst particles are surrounded by ionomer. So ionomer is essentially a polymer. So, and the polymer have these phenyl rings inside, and these phenyl rings, they actually interact with the catalyst particle and reduce the kinetic activity. But before that, I would like to give you a little more background about alkaline membrane fuel cell. I have already said, like in alkaline medium, we can use transition metal as a catalyst, which are much cheaper than platinum. And another advantage of this system can be we can use small organic molecules like such as ethanol, which is a bioproduct, and without so this one has a better kinetic performance in alkaline than acid, acid fuel cell. And all these options, such as like solid alkaline fuel cell, dimethyl fuel cell, direct methanol fuel cell, direct ethanol fuel cell, direct ethylene glycol fuel cell, all these fuel cells can be based on the alkaline membranes. So, and they have different cell voltages. However, I'm not going to talk much about those electrochemical reactions here. So this is the schematic of fuel cell assembly, where the most important part is the membrane electrode assembly, which we call MEA here. So how do we make it? So we have this gas diffusion layer, which is essentially a carbonaceous material. And on the top of it, we coat the catalyst layer, and then we sandwich these two catalyst layer membrane with these two catalyst layer. And this is how we make MEA. And the bipolar plates are here, and they have this serpentine flow channel. So once you keep this MEA on top of it, there will be a gas passing through here, and that can further penetrate into the electrodes where the catalyst such as platinum are there, and along with ionomer. And this is how fuel cell hardware looks like. So what you do is you just combine and pass the gas from here, which will exit from here, and then there is another side where the oxygen or hydrogen will pass from here, and which will exit from here. So this is how assembly looks like. And so once you assemble, how do you know that like how your cell will perform, and then how you gonna gauge the performance of your fuel cell? So usually we run the polarization curve, and the polarization curve looks like this, where our theoretical voltage is 1.23 volt, which should be here, but this is the ideal system. But in reality, it doesn't work that way, because we always have some kind of resistance, and that resistance first comes from the kinetics of catalyst, and because of that we see this loss here. And after that, it is kind of stable until this higher current density, because here the kinetic losses are not dominant, but we have the ohmic resistance, such as the membrane resistance. And then in this region, there is a gas transport issues where we are drawing more current, but the gases what we are providing is not enough to generate that much of electricity. And so because of that, what we can say that this region where, especially this region, just in the middle of ohmic polarization region, that is the region where we get the higher fuel efficiency. And this way, if we go this way, then we will have the higher power output. But then this is how the polarization curve looks like. Now I will begin with the my topic here. So the proton exchange membrane fuel cell is kind of a state of the art, but then it requires platinum catalyst. But alkaline membrane fuel cell is not well developed, and it shows the lower performance, but it has the ability where we can use the transition metal catalyst. So a lot of people, they were researching about the HOR, like hydrogen oxidation reaction, and they came to a solution that there are like several issues, such as adsorption and dissociation of H2 on the catalyst surface, or binding energy is low for hydrogen, and hydrogen on platinum, and there were like other issues like cation hydroxide water layer adsorption on the surface. So what it was look like. So in the beginning, the performance of fuel cell, let's say the platinum based fuel cell, looks like here. So performance seems to be lower, but then if you use the platinum ruthenium cathode catalyst, you will see that the performance is now gone up to pretty good. I mean, this is like comparable performance with the proton exchange membrane fuel cell. So people come up with the mechanism like why we are getting like better activity with the platinum ruthenium, not with the platinum. So some people said that is oxophilicity of ruthenium, and some people said that is weak platinum and hydrogen adsorption binding energy because of the ruthenium. However, when we tested these two catalysts in NaOH, and what we found is like their intrinsic activity here were pretty much same. The only change we were seeing was in the omega or mass transport region. And also the performance, if you look at this, the kinetic performance of these two systems with these two catalysts were pretty much same. The only difference was coming here. So we were like, how we can investigate. And at that time, we were using this as a membrane, this polymer as a membrane and ionomer. So what we did was we tried to simulate this membrane by small molecules. So this is a benzyl trimethylammonium, and what we did was we used this solution to run the RDE experiments, and what we found is that again intrinsic activity at very low potential is same. However, with the increase in the potential, we see that the activity of platinum catalysts are really low compared to platinum. So this tells that the platinum rutheniums are unaffected by the structure like this backbone. So why we have lower activity in this solution like benzyl trimethylammonium solution? So we run some DFT calculations and calculated the adsorption energy. So the higher negative number tells that this is kind of spontaneous. So if you look at the platinum surface, so the adsorption for this parallel position, which we call like phenyl adsorption, has very high like tendency to be adsorbed, and on the platinum ruthenium that tendency is lower. So that tells that if we use the platinum ruthenium, we can have a better activity, and that way we can improve the performance of fuel cell. So further, these were like with the small molecule, and we cannot do RDE using polymer-based material. So what we did was we developed the microelectrode setup, where we have ionomer coating on the microelectrode, and there is a connected platinum counter electrode. And where here we can do either HOR or ORR, what the things we decide, and then the potential will be like this will act as a reference electrode. Here we will bubble the 6% hydrogen in argon continuously here, which we consider that as a 0 volt here. And with that one, we can calculate the voltage at this interface as well as the current. And this is the data what we get. So if you look at this PF PMG anion exchange polymer, which has a very little phenyl group in the structure, have much better activity, HOR activity. And then with the increase in the phenyl, that activity goes down. And the same thing with the PP-BTMA, which has the highest amount of phenyl rings in the structure, has very low kinetic performance in microelectrode studies. And then what we did was we repeated the same experiment with and compared the platinum and platinum ruthenium catalyst, and we found that platinum ruthenium is better. So we wanted to know whether this improvement in RDE kinetic activity translate into the fuel cell performance or not. So we ran the fuel cell performance. As you can see here, the kinetic performance in the beginning at lower potential are same. However, with the increase in the current, we see the clear difference that platinum ruthenium outruns the platinum catalyst. So now the question comes like, does it like the phenyl adsorption also affects the proton exchange membrane fuel cells? So answer is yes. So if you look at here, these two graphs are for platinum and platinum ruthenium, and with naphion, which does not have any phenyl group in the structure. And these two are from the sulfonated polyphenylene polymer, which has a lot of phenyl rings. And you can see that clearly that the performance is much lower for these polymers. So we can develop several mitigation strategy. We can actually reduce the overall phenyl rings in per gram of polymer. So what we can do is we can introduce the instead of aromatic backbone, we can introduce some aliphatic backbone here. That way we can reduce the overall phenyl content in the polymer backbone. So if you see here, this is the platinum, this is platinum ruthenium, and this is this polymer on platinum ruthenium, which has a much better activity, and that also translate into the higher fuel cell performance. So if you look at this one, this shows the high performance, but this performance is still not as high as the proton exchange membrane fuel cells. So what we did was we did like some DFT calculations and tried to modify the electronic structure on the phenyl rings. And what we found is if we if we combine this, let's say phenyl ring with the polyfluorane, then this structure is kind of a little bit tilted. So this doesn't adsorb right away on the platinum surface. So that's why the adsorption energy for this small molecule was much lower than the biphenyl molecule on the platinum. And the same thing we see with the platinum ruthenium. So we are expecting that this might improve the overall fuel cell performance. And before that, we ran this micro electrodes with this one, and as you can see, with the biphenyl polymer backbone, there is a lower activity, and then FLN, which is the fluorane, polyfluorane, has a better activity in micro electrode, and that translates into so these two, pink and red, are for biphenyl, and these two are for polyfluorane on different catalysts. So this one is on the platinum ruthenium, and this is on the platinum. So we see that there is not much difference in platinum and platinum ruthenium catalyst if we design the polymer backbone. So this actually gives us hope, and this performance is also high that this system can compete with the commercial proton exchange membrane fuel cell. So same thing here, when we reduce and increase the platinum content, we see the different performance, but this performance were competitive with the proton exchange membrane fuel cell. And if I put the state-of-the-art proton exchange membrane fuel cell, how it looks like, the performance here in the blue, I don't know the color, but I think this is the performance which state-of-the-art proton exchange membrane fuel cell have. And if you look at this blue curve here, it's actually comparable. So now the time came where anion exchange membrane fuel cell can compete with the state-of-the-art proton exchange membrane fuel cell if we can develop the more polymers or like membranes and ionomer where we can avoid the phenyl group adsorption. And so now the system works. So the next step would be developing the non-precious metal catalyst. And I think our group here, we have like a lot of work going on currently where we are developing non-platinum group metal catalyst, such as iron and cobalt based stuff. So hopefully there will be some breakthrough in the future. So now I have so far I have talked about the fuel cell. Now I want to talk little more about my own project where we are developing the iron pyridyl imine based complexes for non-aqueous redox flow batteries. So as I said, like in the introduction, so aqueous flow batteries are limited by 1.8, maximum 1.8 volt, because beyond that there is a water splitting reaction happens on the surface of electrode. So in order to avoid that, what we can do is we can replace the water with organic solvent, where then that way we can actually go with the redox material which has a higher cell potential, such as chromium acetylacetone, which has a 3.0 of standard potential, or manganese or ruthenium. So these all have like higher than 2 volts of cell potential. So with this one, like they can operate once you have the higher cell potential, so you can calculate like the with the higher cell voltage, you can have the higher energy density. But the problem is this is like this system is not yet fully developed, and it's in the experimental stage, and because of that we are suffering from the lower solubility. And if you have the lower solubility, definitely your energy density is going to be low. So we are working on improving the solubility. And before that, I want to show you the current status of non-aqueous redox flow battery in US. So Department of Energy has long-term capital cost target for the energy storage, not for the flow battery, but for energy storage. So what DOE wants is the cost of unit for per kilowatt hour should be between 100 to 150 hour. And this is also very challenging cost target. So it can be any system which, if you can provide this like in this cost target, that those systems are going to be future energy storage systems. So here is the aqueous and non-aqueous cost factors here. So based on after analyzing all this this graph, we can consider that non-aqueous flow batteries can be successful only if active species cost are limited to $19 per kilogram and the solubility of redox species are more than 2 molar. So, but then this is very challenging cost target. So our group is trying to increase the solubility of our material as well, and also we are trying to increase the decrease the cost. So how we can decrease the cost? So I have shown you the example of vanadium, ruthenium, and also like lithium ion batteries are there as a competitor. So if you look at the cost of these metals per pound, you will see that the cobalt, vanadium, lithium, nickel, manganese, they all are kind of expensive compared to iron. Iron, you can't even see if there is iron exists or not, because iron is like $0.03 per pound. So it's like one of the cheapest metal we can have. So that's why our focus is to develop some iron-based chemistry, which can be easily synthesized, expensive and scalable, and they are reversible, and they show the reversible behavior in the bulk electrolysis, and then we can use those in a non-aqueous flow battery setup. So this is the like ligand-based, iron-based iron ligand system we chose, where we started with the pyridine 2 carboxaldehyde, and with like a 2-step reaction, we can synthesize iron methyl pyridylamine triplet, which is deep purple solid, and it shows the why we chose this iron pyridylamine system is because it is reasonably inexpensive, and once let's say if this chemistry is successful, we can synthesize this material in a larger quantity, and because this is bidentate ligand, it can form octahedral geometry around iron. So this has some attractive properties, and that's the reason why we chose this for our study. And we ran this in cyclic voltammetry, and as you can see, the first redox ligand-based redox event is reversible, because the ratio of ionic anodic and cathodic currents are 1, and the same thing here. The reaction associated with the iron +2 and +3 is here, and that is also reversible. But the second redox event is not reversible. However, in future, if we modify this one and if we make it reversible, then we can have the cell voltage up to 2.6 volt, which can give us really high energy density in fuel cell in flow batteries, and that is why we need to work on this. But because these two events are reversible, this is a candidate for symmetrical redox flow battery. So what we did was we did the bulk electrolysis. We tried to charge and discharge the iron species here, and as you can see here, it charges and discharges really well, and we did not see any kind of loss in the coulombic efficiency as well as the energy efficiency. So what happens when we try to charge discharge the first redox event associated with the ligand? It looks like the charge and discharge profile looks good, but when we see how the charge and discharge efficiency capacities are going, we see there is a slight decrease here. So that tells that it might not be stable, like fully stable in the system. But anyway, we tried actual flow battery setup, and what we found is like here is the discharge profile and this is the charge profile. So when you charge the cell, it stores the energy here, and then when you discharge it, it provides the electrons and like energy in terms of electricity. So we did not see like significant change in 15th cycle, but if we are looking at the application for large scale energy storage, then 15 cycle is not enough. It should be close to 10 to 20,000 cycles. So I would say this is still early research, and our complex, whatever we synthesize, is not yet stable, but we are working on it. And right now we are using only one electron in our system, and because of that, we are here. Like our energy density, theoretical energy density is around 30 watt-hour per liter.
அதுல முதல்ல நீ வாட்ஸ்அப் வெப் கனெக்ட்
if
பண்ணு.
we start using 2 electrons, somehow, then we can boost the energy up to 40 watt-hour per liter. So with this one, I would say we are we have done some work with the iron-based, like in development of iron-based redox active material. However, there is a long way to go because this field is pretty new, and we are every day making some progress in this field. And key challenges are like, as I said, like still long-term cyclability and increasing the solubility of these molecules by ligand engineering to be, like for the practical applications. So I think that's the end of my work also. And here I want to acknowledge the funding from FCTO as well as the Los Alamos National Lab. And here are a list of my colleagues who helped me in this work. And I would be happy to take any questions.
Very good morning, sir. Actually, it's good evening for you, actually.
Mm-hmm.
So, one thing I came into my mind is you are using a polymer for
Uh-huh.
the proton exchange membrane, right? So, can we use polystyrene polymer sulfonated?
Yeah, so if you look at this one here,
Yes, yes.
this is polystyrene based anion exchange polymer. So we can definitely use polystyrene based polymers, like sulfonated polymers for proton exchange membrane fuel cell. But there is a problem, like slightly problem with polystyrene is that it's brittle. You cannot form membrane. So what people have done, people synthesize copolymer, like polystyrene with the divinyl benzene or with some other kind of copolymer, and those polymers they can be used in fuel cell.
Actually, the reason for raising this question is, can we the thought of using the waste polystyrene that we are disposing, so can we reuse that waste polystyrene into make it some kind of membrane to make it useful for the fabrication of fuel cells? So
So
that's what my question raised.
yeah, so it might be challenging because using polystyrene as it is, I mean, it has lower properties and especially the mechanical property. And when we are talking about the long-term stability and durability in the fuel cell, I don't think recycled polystyrene might work as it is unless we find another application, such as we can form a a composite material for gaskets, something like that. We can definitely use then styrene.
Oh, oh, oh. Yeah, thank you very much.
Mm-hmm.
One question.
Hello.
Yeah, I'm Dr. Shadre.
Mm-hmm.
Just one question.
Sure.
I was doing some postdoc in West Virginia. We were using Department of Energy gave us a program on setting up alkyl aryl sulfonates. We synthesize we cook the compound in the laboratory, and then we use it for enhanced oil recovery. That has become a part of energy program, actually. In fact, it is not electrochemical, but a different program. I just want to know whether you're used to so many electrodes. Can you think of some sulfonates being used? Sulfonates?
You mean sulfonated polymers?
Oh, yeah.
So I don't know if you know James McGrath or not. And so James McGrath's student is Yusong Kim, who has been who has developed a lot of polyethylene based sulfonates, and he has done a lot of work in proton exchange membrane fuel cell. But those whenever he was working with those polymers, he will never get good performance. And so the reason is phenyl adsorption on the platinum particles. So that we recently came to know that in 2017, when I was doing this study, that's when we realized that the real culprit is not the polymer itself, or not the high IC or low IC, but culprit is the phenyl adsorption on the platinum surface, and this is why we don't get good fuel cell performance. But definitely, as like fundamentally, all sulfonic acid polymers can be used as a membrane and ionomer in fuel cell.
Now, how do you compare it with your platinum and ruthenium? Is it possible? Is there any way you can compare it? I mean, I'm talking about the efficiency.
So comparing like platinum and ruthenium efficiency is slightly hard because they both have like different adsorption properties.
Yeah, adsorption. Yeah.
So this is why let's say the molecule what we developed here. So this one has almost similar adsorption properties on platinum here and platinum ruthenium here.
Okay.
So if the absorption properties are similar, then we can compare the fuel cell performance, which you can see here. But other than that, is going to be challenging.
Yeah. One more question. How much of American industries have taken up your project to, formalize some of this as a sort of products for it?
In China?
No, in US and United States.
In US. Okay. So that's actually always I mean, already like how research and industry work.
Yeah.
So we always have this trust issue, like they don't trust us and we don't trust them. We think that they're gonna make a lot of money from our things and we won't get anything. And the same thing, they think like, whatever you do in the lab might not work in the real world. So
I know.
Yeah, we have very good collaboration with Nikola and also like GM on fuel cell side. So I would say there is a healthy exchange going on between Los Alamos fuel cell research and industry.
How much of Indian industries are showing interest in your product? Excellent work you have done. Excellent work. How much of any Indian industries are interested in this?
So I am not sure because I have never approached to any Indian industries for any commercialization in any commercialization efforts. So I cannot comment on that. But based on my whatever I hear from friends and whoever are working in the working in India in in this field, according to them, there is some interest in battery technology, but I think fuel cell technology will take some time.
Last question. When you talk about absorption, there is what is called Frankel and Schottky effect. Absorption energies are estimated by the Frankel and Schottky effect. You might be knowing about it. How much it is going to be for platinum and ruthenium absorption?
I actually haven't thought about it.
Yeah, because the reason is Frankel-Schottky effects will tell you when the absorption taking place, what are the areas in which they do. Some of them are blocked, some of the areas they're taking up. So you have taken up platinum ruthenium. Is it on the basis of the absorption qualities much faster than others, or randomly you have taken?
So this is like a DFT calculation done by our collaborator in University of New Mexico. So what I think, based on my discussion with her, what she did was like these platinum particles, they have this certain electronic structure and tendency to attract the electron cloud of phenyl rings, and because of that, it will stick to the platinum surface. And I exactly don't know if what equations he has used. So what I have is like adsorption energy numbers with me.
Thank you very much for an excellent lecture. I learned a lot.
Thank you very much. Yeah.
Thank you.
I thank our dignitaries for completing the technical session 1. May I now invite Dr. S. Geeta Madam, Controller of Examination and Associate Professor of Chemistry of our college, to chair the technical session 2. Please, Madam.
So can I stop sharing my slide? Is it okay?
Yes, sir. Yes, sir. Yes, sir.
Sure.
Shall I start, Kalpana?
Yes, ma'am. Yes, ma'am.
Very pleasant morning to all of you. I deem it as a big opportunity to introduce the resource person for the second session, Dr. Vallam Sundar, who is Professor Emeritus in the Department of Ocean Engineering, Indian Institute of Technology, Madras. Sir is having 38 years of teaching and research experience. His field of specialization includes coastal engineering, port and harbor structures, harbor development, fluid flow problems, tsunami mitigation measures. Sir is a member of various professional bodies inside India and abroad also. To cite a few, International Association of Hydro Environment Engineering and Research, American Society of Civil Engineers, Chairman Executive Committee of IIHRAPD, member the Royal Institution of Naval Architects, London, UK, member Coastal Research Foundation, USA. He is an expert member in various technical committees. Coming to his research work, Sir has completed 12 projects sponsored by different government agencies within India and 7 international projects like Indo-German projects sponsored by DFG and Volkswagen Research Foundation, Germany, and DST support projects with Russia. And 7 projects are ongoing now. Sir is a consultant for several projects related to port and harbors, coastal engineering problems, and completed about 300 consultancy assignments. Sir has been a thesis advisor for 27 PhD, 13 MTech, 17 MS degrees. Sir has authored 3 books related to ocean engineering, published in international edition by Wiley, and also a co-author in edited book chapters. He has many awards to his credit, and I will read out a few. Maritime Award for 2004-05 by Ministry of Shipping, Road Transport, Ministry of Shipping, Government of India. Honorary Doctoral Engineer Award from University of Wuppertal, Germany. Professor R.J. Gade Lifetime Achievement Award. Sir has more than 533 publications in all international and national journals and conferences, publications. In international and journals and conferences alone stand for 400 number. Sir has been a visiting professor for University of Wuppertal, Germany, and visiting professor, Department of Civil Engineering, Norwegian University of Science and Technology, and expert member on the International Panel of Experts. And he has been a visiting professor to various other countries like Singapore, Mauritius also. And he has been a member in the various reputed journals related to ocean engineering topic, Journal of Coastal Research, Ocean Engineering Journal, Applied Ocean Research, Journal of Hydro Environment Research, and so on. And he has completed 2 course modules titled Breakwaters and Coastal Erosion and Protection, sponsored by Center for Continuing Education, IIT Madras. Lectures on 2 postgraduate degree courses, such as Wave Hydrodynamics and Coastal Engineering, which are live streamed in YouTube. With this a very brief introduction, may I invite Professor Vallam Sundar to chair this, to give his lecture. Sir, please. Kalpana. Thank you, sir. Welcome, sir.
It's okay. Thank you very much for introducing me. And towards the end, you said the brief introduction. I think, I don't think it was quite brief. It was quite lengthy, in fact. Anyway, I thank the authorities concerned for giving me an opportunity to present this lecture. And of course, I have come in place of Professor Sanasraj, who is my colleague, and he is held up for some urgent work, and so he asked me to step in. So the topic assigned to me is energy from ocean and green chemistry. The green chemistry, I'm not very sure about green chemistry because I'm just standing in or sitting in front of experts in chemistry. So I don't think I can really make a headway into this chemistry. But anyway, I'll touch upon the energy from ocean. So what I'm trying to, the organization of my lecture is as follows. I'll just briefly introduce. I see the audience, I think there are a lot of students also. So I will not be going into the mathematical aspects, and I'll just touch upon, and later I'll tell you what about the mathematics or other aspects. Let's see how it goes. So I'll start with an introduction, operational wave and tidal plants, tidal and wave power potential. How do we stand? Then developments in India, in brief, because we were asked to prepare a concept report about a few years back, which we have done. And then we will try to just, I may not be looking at this. I will just briefly tell about the wave energy conversion, but may not be this, but some of the aspects, like for principle, I'll touch selection. Okay, I think I'll be able to touch most of these things. And then I'll try to summarize. And towards the end, only this morning, I try to rope in the ocean acidification, just to give you some idea.
Excuse me, sir. Will you please
Yes.
share your screen? Share your screen.
It's not there. I already shared.
No, sir.
Are you able to see
Now
that?
we can see, sir.
Yes, sir. Yes, sir. Yes, sir.
Sorry about that. Okay. Now the different types of ocean energy we have are from the ocean currents, offshore wind, which is very much discussed these days. Then ocean thermal energy conversion, that is utilizing the difference in temperature from the surface to the deep ocean. This is a complicated stuff, and in fact, IIT Madras, we did we were involved in a pilot plant, and it was of Kulasekara Pattanam of Tamil Nadu, but unfortunately it did not work out. And then we have been having a lot of conceptual designs for tidal energy, tidal power, and not much of work has been done in the salinity gradient, that is the salinity difference in the ocean, because wherever you have kind of gradient, this gradient can be utilized for generation of power. This is a basic concept. Then finally, we are very much into wave energy, and I will be concentrating more on the wave energy aspect. So then when you just let's have a overview on the wave and tidal power potentials, because before we venture into any kind of technology, we should understand what is the viability. And viability is assigned through or estimated through the available potential. So for example, tidal currents. Tidal currents, for example, you know that Gulf of Cambay has a very large tide elevation. That I will also tell you what is the basic difference between wave and tide in the due course. Right now, you take that tide is just an oscillation of water surface elevation in the ocean. That is, the mean sea level itself will go up and will go down, and then again come back to the mean sea level. So because of this rise and tide at different elevations within the ocean, there can be some flow taking place from higher tides to lower tidal elevations. So this is a natural current which is flowing, and if we can have something like a moving part, as you can see here, and that can generate power. So this is one concept. Then the other one is the estuarine. So wherever you have water, you can store it, raise it, and then use that head of water to generate electricity, similar to our dams. Then finally, waves. This has a very good potential. In this case, you have environmental impacts, high capital costs, and limited number of sites, because mostly we'll be concentrating on Gujarat area. And here the prospects are good, but you don't know, once you put it inside the deep ocean, we don't know what happens. The maintenance also going to be quite difficult. These are all some of the issues. But whereas here the good in terms of medium and long term, uncertain for short term, but there are some ways of addressing this also. So when you look at the different major operating plants, operating the tidal and wave power plants. So there are two slides. One is initially I'll touch upon the tidal power plants. Major operational tidal power plants are these things. One is Korea, South Korea, France, Canada, China, and Russia. Of course, we don't have anything. We are still talking about the Kalpasagar project. Again, it has got some life. I hope something will come through. Let's look at it. I'll try to project about the Indian context at a later stage. Then pilot project on the tidal stream, that is the current, tidal current. So there are a few things, UK, Norway, UK again, UK in several locations they have installed this, and they are quite happy with it, although there are some issues concerning, because as I said earlier, okay, major wave power plants. I think there is. I think the mics have to be controlled. I think someone is making some noise. I think you can easily control that. Okay, major operational tidal wave power plants. Mostly it is what is called as oscillating water column principle, which I will explain later, because there are some natural energy, natural scenario where from which you can get energy. So of course this is in China, Scotland, and be happy that India is also appearing here. And it was our department when I joined in 81, the Department of Ocean Engineering, so one of the youngest youngest faculty member. And at that time only they were talking about ocean engineering. I did not understand anything about that at that point of time. But then I got involved quickly, and then we started working from 1982 and early 90s. We had a pilot power plant. I think there is some problem. Okay, now what about the developments in India? So as I said earlier, 1980 we started. Then 1990 we had the first OWC. I'll tell you what is OWP patient. In 1990 we had installed a pilot power plant to extract energy from the ocean waves, and this was in Kerala, Trivandrum. And then we also demonstrated there is another institute which is called as National Institute of Ocean Technology, which originated from IIT Madras, and they have tested what is called as bent ducted buoy. That is, it has a bent opening at one end, so it will be moving, or it can be stationed in one particular place, and then the oscillations of the wave elevation can be utilized to generate electricity. Now we have the other one, which is Atlantic Gulf of Kutch. The capacity is as indicated there, and this is still in discussion stage. We have to wait when this will take off. Now, the status of existing tidal and wave power projects in India. Kalpasagar, yes, the capacity is given here and yet to start. We have in the pipeline. Gulf of Kutch, capacity is here. Concept, it is only a conceptual design. Initially, we had in some of the creeks, but then the idea was to have a tidal barrage, like similar to what in Kalpasagar, but this is dropped now. For when you look at this one, I mean the wave power, Viridium already we demonstrated it works. It works, the concept works, but then when you look at the cost benefit aspect, then there are a lot of ifs and buts. And I'm going to address that, how we are now thinking of having a multifunctional wave energy power plants. This is in the recent times we have started working on it. Then this one, this backducted boy, a boy, which I just now explained. This was demonstrated, only demonstration is over, but so still we are in infant stage, I would like to say. And we have done a lot of work in IIT Madras, in our department, how to improve the efficiency of the OWC before it is implemented in the field. So we had completed recently a major project with supported by Norwegian Science Council of Scientific Research, and the project lasted for about 3 years, and then we have done some lot of studies, and then it's going to be looked into further. Let's hope something comes up. So as I said, I have combined both tidal power and wave power. These are the only two things which I am going to concentrate. Let's look at the tidal power potential in India. So what is happening here is, what exactly is a tide? Oh, there is some problem. Okay. Now you see what is a tide. Look at the animation. So on the right side, you see the land, and on the left side, you see the ocean. In the ocean, you have you have heard of what is called as mean sea level. So mean sea level itself will be going up, then come back to mean sea level, and then go to low tide. So this oscillation of the entire water level in the ocean is called as the tidal range or tidal tide. It is caused because of the tidal attraction, because of the gravitational attraction between the three celestial bodies, sun, moon, and the earth. So you know about Amavasa. Amavasa, you see that the water level is going to be rising. Okay. An overview of our approach for estimating the tidal power potential. So the tidal level at various locations along the Indian coastline is found using the National Hydrographic charts and WX tide, and we perform a harmonic analysis. I hope there are some mathematics guys are also in this audience. The site conditions like tide range, current speed, water depth are the governing criteria for energy, and all these things have been estimated, and we have come to the estimation of the tidal power potential. So the tidal power potential along the Indian coast looks like this. So the different colors explain. So we don't have much of a tide in the southern part of Kerala, along the Kerala and Tamil Nadu. As you go further towards the north, on either side, you see the tidal range increases. For example, here of Bengal, the tidal range will be of the order of about 4 meters. 4 meters, you can imagine, it's slightly more than our headroom. Okay, so much of head of water is freely available, and it keeps going up and coming down. When it goes up, you have the necessary head, and that necessary head can be used for driving the turbine through which you can get the electricity. That is a principle on which the whole thing works. And when you look at Gujarat, and that is the area which is discussed more, because that has the highest tidal range. It has about 11 to 12 meters. The highest tidal range in the entire world is in Canada. It's a place called as Bay of Fundy. So these are the tidal range approximately, which is given here in the term as a now. So that shows how the tidal range is looks like, and we need to concentrate only around Gujarat or maybe West Bengal, and lesser than going south. There's not much of potential. Then now assessment of wave power potential. First, we have to assess the potential, and then we look at the concepts. how big a wave can be. An ocean wave which you go and see along the beach, you simply see that it breaks because whatever energy is there in the ocean wave, it slowly, gradually loses because of the seabed. The seabed is sloping, because of which the energy is lost, and slowly when it comes to the coast, it breaks. What you see is whatever energy contained in the waves are broken, and after breaking of these waves, you have a gentle uprush of water over the beach, and that's the reason why you go and stand along the beach boldly. But I don't think you can go and stand in this kind of wave. But this guy has the enough experience is coming out. So much of energy is available in the ocean, that is through waves, and this can be tapped. How will next? And another thing, the waves are oscillatory motion. The oscillatory motion, in the sense, when the waves are moving, it can be described as a sinusoidal motion. For example, the pendulum of a clock. Okay, it from a mean position it goes, then comes back to mean position, goes back like this. Even the tide is also an oscillatory motion, but the tide has a long duration. But whereas the waves have a shorter duration. So when you are able to sit on a wave, this is what you are likely to experience. That is, you will be undergoing a kind of an elliptical orbit motion. So this is the kind of oscillatory motion which we need to tap, and so that you can have a linear motion or linear driving of the energy. That is the crux of the problem. Because when you see, when the crest is there, you will have more energy. But when the trough is there, there won't be much of energy. So this difference in energy, we have to make sure that the turbine will be rotating in the same direction. When the crest is there, it will rotate in this direction. But when the trough is there, it should not rotate in the opposite direction. It should move in the same direction. That is where the challenge was. And that the challenge was for the mechanical engineers in order to design the turbines. So which has been done. So when the waves are propagating from deep to shallow waters, this is why you will be standing somewhere here. What you intend, what you see is the energy that has been propagating, the wave height keeps on increasing, and then it breaks here, and then you have a gentle uprush of water. So you see that the waves that can be, the energy can be extracted from waves anywhere here, somewhere here, or in deep waters. When you go deeper waters, the cost of implementation of the project exponentially increases. So you don't go into deeper waters, and so you just restrict yourself. For example, the Kerala project, the pilot plant was restricted to 10 meters water depth. Now you see the distribution of wave energy around the globe. So we do have some amount of energy on an average. This is on an average. So for example, see here, this is the area where you have a lot of energy. So these countries are doing, they have a wide experience on handling this wave energy plants. For example, if you look at Google and see, Europe has the maximum number of wave energy plants, so followed by maybe to a certain extent along the east coast of west coast of Americas. So then we move on to the present approach. So as I said about the tidal energy potential, now we are looking at the estimation of wave energy potential. So this we have what is called as a, I will not go into the detail, but believe me, this was a well accepted practice to get the wave data. So we have gridded wave simulation. We have simulated the wave climate over the entire Indian Ocean for about 5 years using public domain software. It is not nothing like we would like to claim any credit to this. This is what is called as a WAM. It's a wind wave model. So we use that and we generated the wave power potential. The wave power potential is as shown here. So here you see that you have some of the locations. It is not like very clear as in the case of tidal power, because the tide is very, very clear towards the end. either east coast or west coast, you towards the north, you have maximum power. The tidal power, it keeps increasing as you go towards north, but that is not the case in the case of wave power. So you need to be, although the wave energy is quite easy to extract, but there are a lot of issues concerning the selection of site, because because it's not a uniform kind of variation of the power. The main criteria for selection of site selection strategy is available of wave power, local demand of power, not only local demand of power. Now, if you go in for standalone wave energy plants, then you are in for trouble, as we have done in the case of the pilot plant of Kerala. If you can combine it with some other multifunctional benefits, then wave energy would be a very good thing. So instead of a local demand of power, plus you have to add on some things, then it will be good. The device selection strategy, erosion prone. So what we are addressing is one of the most widely talked these days, the coastal erosion, the sea level rise. The sea level rise is also contributing to the coastal erosion. In fact, there was a one of you, if you can contact me, I think I will share a link with the organizers so that they can share it with all of you. Yesterday only we got it from the science section, where we have clearly explained how serious is the coastal erosion. Now, in this case, we are trying to integrate wave energy plant with coastal protection system. That is quite interesting, and we have initiated for the first time in the entire. I'm very proud to say that IIT Madras has taken the lead in this particular field. Now, wind dominated combined offshore. So now people are talking about wind power. Again, it is Norway, UK, etc. They have taken much lead over all other countries, because the potential of the wind, offshore wind, is very high. Now we can also think of combining a few sources of energy, maybe wind and wave power can be combined. So this is also, some of my colleagues are also addressing this. So when you look at the energy conversion, so I'm going to concentrate more on wave energy conversion, which is viable, and input energy from the waves. So primary energy conversion into energy, it is in a pressurized air, or water is pressurized, or hydraulic oil is pressurized. I'm telling only the principle. Then the secondary conversion is by the turbine or hydraulic motor, mechanical energy by rotating shaft. Then finally, this will be utilized to generate electricity. Now, where are the energy losses? So energy from the waves, you have abundance of energy in the waves, easy to calculate, and it's a clean energy, no adulteration. So primary conversion, you have some loss when the energy from waves is converted into some kind of a working fluid, and that working fluid can be air or water or hydraulic. So what I'll be concentrating is about the air. Oscillating water column device is about the air. So here, when this is from this to converting, getting the air, that is going to be the output, you have certain amount of loss. Then again, from that to the turbine, there could be some loss. From the turbine to the electric journal, because turbine already you have some mechanical parts, and from the turbine to the electric, again you have some kind of loss. Again, from electric generator to the grid, again there could be some loss. So there are so many losses. So what is that we can do? What is that our department can do? We wanted to work more on this aspect, at least all these aspects, but mostly we are concentrating, at least my group is, we are concentrating on this aspect. One of my other colleagues group is concentrating on this, another is concentrating on this. So I will not be going into these aspects. I will touch upon my own field of expertise. So wave energy, so what are the different types of wave energy? Is it a new thing? No, it's not a new thing. It is in existence for several years, but unfortunately we have not bothered to really look at it. Now people are talking about of energy crisis. So now, using one of the following principles. So one is focusing of wave energy. Based on natural topographical features, water can be stored at high elevation, and the potential or energy of the water stored can be used for rotating a turbine, similar to our hydroelectric power, hydroelectric stations, dam engine, from the dam reservoir, you have the head of the water, and then that will run a turbine. So then the pressure difference between the free surface. This is what is called as oscillating water column. I will come back to that. And then relative buoyancy, which will also be explained later. So basically, we have terminators, attenuators, point absorbers. These are the three major classification based on its size also. These devices are assigned parallel to the wavefront. Waves are coming, you are standing somewhere here, this is the shoreline. Waves are coming in this direction. So you have a structure placed in this direction, and this is called as terminators. You are terminating the waves by extracting the energy into this structure which you have installed. Okay. Then the other one is the attenuators, lies in the principle of direction. So wave is coming in this direction, it is aligned along the wave direction. So along the wave direction, you will see what happens. So I will explain, which was demonstrated by a device called Alamos in Portugal, and they found it quite interesting and promising. Then finally, I'll talk about the point absorbers, wherein you can have a number of points absorbers, and the wave is coming in this direction. It can be a group of structures or floating things which can generate electricity. One of my PhD student is right now working on this concept, and we are interacting with an university in Australia. So now, as I said earlier, how do I understand this wave energy extraction? Where does it available? Now look at this OWC in nature. See, look at this. So there is nothing, no one is creating anything. It's a natural thing. So water is gushing into this hole, and this is the air. This is a fluid that can be, so you see that it is there for some time, and then it dies down. So there is a gap. It comes in intervals. During that interval, the turbine should be operating in the same direction. It should not come back. So that is the concept, and that is very important. So this is what is called as oscillating water column. Now you look at this animation. The waves are coming in. You have a structure like this on the coast or in the ocean. So then you see that the waves are coming and up and down. And then this is the area where you have that air column, and that air column will be moving up and down. Whichever direction it moves, the turbine will be rotating in the same direction, only one direction. And once the turbine rotates, then it generates electricity. So the concept is very simple. But then what are the losses? And that is where we need to understand. So that is what is called as oscillating water column. Now you see that these are the point absorbers. You have a number of them tied to each other. So the buoy will be moving up and down when the waves are moving, and this motion it's something like pumping of energy, and that can be utilized. Now this is what is called as the Alamos, wherein you see that this is from Portugal. So you can just I think it's more or less self-explanatory. So you see it's something like a snake in the ocean. So it moves up and down. You have joints, and these joints will be working due to the waves. The external force is the waves, and that is going to act like a piston, and this piston is going to send energy to the pumping station. So this is a simple concept, and this was quite successful. And in fact, I had the opportunity of meeting the inventor of this, and he's quite old, and then he looks very promising, and it has demonstrated its application. Okay. Classification according to location, shore-based, near bottom, or floating. You can also have floating oscillating column. Whatever the device I showed, it can be anchored to the, but it has not been investigated thoroughly till date. But there are only concepts, but it is only in the conceptual stage. Bottom seated, yes, we have done a lot of work, and submerged, not from this is not going to work. There are some concepts, but not so promising. So classification, again, you have, there are different types, but I will not go into all these details, but I will, moreover, I'll try to concentrate only on this. So advantages of this system is the turbine is the only moving part. It can be easily integrated with any coastal work. For example, it can be integrated with a harbor. I'll come back to that integration part. Then operation is land-based. It's very easy. Maintenance is also easy. And as I said, the moving part is only one, that is the turbine, which is shifted to the top above the water surface. So maintenance is easy. Disadvantages, the radial flow have more impedance, because the turbine also will be rotating like this. So the opening depth controls the performance. So this depth also controls the performance or the efficiency. So this opening will be depending on the wave climate. The wave climate is a varying phenomena. So it's very difficult to design this system. Of course, we have made some attempts, and we have come out with some kind of optimum designs. And I don't have the time to share all those things. So here you see the demonstration plant. This is in Vizhinjam in Kerala, just close to Trivandrum, just 5 kilometers from south of Trivandrum, I guess. So the demonstration plant, this was in 10 meters water depth. It was in 10, anything 10 meters. So it was designed, commissioned by IIT Madras, and in the year, I think 1990 or 1992. It is a caisson, which was initially, this is the dimension of a caisson, precast on shore, and then you fix ballasting tanks, and then tow it to the site, and then control ballasting. So the lowering of the caisson also is very important. If you have to carefully do it. So we did one caisson, could not be a successful thing. So first time it was a failure, the second time was a success, and we have demonstrated that it works. Now coming to the differential, so we know that it works. Now how we can optimize this? This is the work which I have done with the Norwegian science. Now when I was in Norway with the Norwegians, wherein we identified different concepts, and these concepts are here. So you can link OWC with a caisson. So this caisson can be for a harbor purpose. So you can berth the structure. So it can be used for a multi-purpose. So OWC, when you are developing a harbor, you can think of whether you can it would be beneficial to have a OWC linked onto it, so that it can generate power as well as serve as a protection measure. So there are other concepts also. I will not go into the details, but this is one more thing where you can have a floating type of structure, the OWC, and this can serve as a small marina. And you can also think of having a slightly deeper waters. You can have a frame structure, and then this can be used as a, earlier what we saw was a caisson. Now we see a kind of a framed structure where this can still be used. And this is for deep water berthing structure, because now when you look at our maritime trade, harbors are all have started handling deep drafted vessels, ships. So they want to go into deeper waters. So when they want to go into deeper waters, these are the concepts which can be thought of. So now when we looked at this work, very promising work, we did a lot of investigation, and we came out with the 2 PhDs, and this entire project was supported by the Norwegian Science Council. And now you see, one of the step was how to control or minimize the loss or improve the efficiency. The wave is coming here, this air column is oscillating, and that air column only we are trying to tap. So now if there is some attenuation, if there is some loss of energy while it is oscillating, that we should try to avoid. So one of the step is, instead of having a vertical like this, why not we have a curved bottom? Or why can't we have a bottom like this? Or why can't we have a bottom like this? So these are some of the things which we had investigated, and we investigated in the lab, and also we measured how much is the pressures, etc. This is from academic point of view as well as a design point of view. I will not go into the details. And then we found that the one with the circular arc, that is this one, was more promising in terms of it improved the efficiency, as you can see here. So efficiency has gone up to about 75%, and still some more work is needed. Not only that, we had to also optimize this spacing, and also this hole. This hole is about, I think it's around 0.6 of the total surface area. I think 6% of the total area. So then, after having done that, the part of the project also looks at this. We wanted to have this as a coastal protection measure. How do we install this wave energy caisson into coastal protection measure? For that, you should understand coastal protection measure. We have what is called as breakwaters, which are aligned like these are structures which are trapezoidal in section, and these are constructed using natural rocks. And these structures are placed like this based on some principle. Let us not look into all those principles, but it works. So an eroding area can all these things you see after building these structures like this, the sand has come and accumulated, deposited here, and the beach has formed. So an eroding coast can not only be prevented from further eroding, but also the detached breakwaters can help in winning the lost beach. With this in idea, what we did is this is in-house. We have a lab where we can test. So this is the rubble bound breakwater, as you can see in plan. We have 1, 2, 3, 4, 5 columns of OWC installed, and we are trying to look at how it is responding to the waves, and whether we got some very useful results, and a number of publications have come out. And as I said earlier, this is the first time it has been done or thought of. So schematic view of a harbor with breakwaters and OWC. This is how our idea would, if implemented, is likely to work. Now, I was because I was asking myself what this chemistry or is going to happen here. I didn't get much because I'm not a chemist. But anyway, I heard from one agency from the US. They contacted us and they were talking about ocean acidification. So I think you are more competent enough than me. But I am only an infant in this area, but we are likely to get it in this field shortly. And if someone is interested, please contact me, and your help may be needed in this regard. And the contact person is from US, in fact. So reduction in the pH of seawater as a consequence of absorption of large amounts of carbon dioxide from ocean by the ocean. When carbon dioxide dissolves in seawater, the water becomes more acidic and the pH value drops. So thought to be a good thing initially, because it leaves less carbon dioxide in the air to warm the planet. But chemistry of ocean acidification, carbon dioxide dissolves in seawater, a series of chemical changes break down the carbon dioxide molecules. You get the carbonic acid, and carbonic acid releases hydrogen ions which bond with other molecules in the ocean. Seawater that has more hydrogen ions is more acidic, and it has also lower pH. So the trends of ocean acidification in the past 200 years alone, ocean has become 30% more acidic. And if we continue to add carbon dioxide at current rates, seawater pH may drop another 120%. This is from the net by the end of this century. That's what is anticipated. It is expected to have dramatic and more mostly negative aspects on the ocean ecosystem, particularly the flora and fauna. And so far, the signs of acidification visible to humans are few, but they will only increase as more carbon dioxide dissolves in seawater over time. What can we do to stop it? I leave the question to you people to ponder over it, and any kind of input from any of you will be very much appreciated in this particular area. So cut carbon emissions, a part of potential solution lies in the ocean itself. The ocean contains an enormous and almost limitless amount of energy, which I have touched upon to a certain extent. And then with this, I have already told, I don't want. So summary, I have touched upon potential sites for tidal energy and some of the works that are in pipeline for our country, and some of the power plants that have been installed all over the globe. And similar thing holds good in the case of wave energy potential, and also some aspects of linking wave energy concept to as multifunctional products. So this is what I was trying to explain. And recently we brought out a book, my colleague, another colleague, Professor Sanasraj, and myself, and he is a postgraduate PDF fellow who is now currently in Japan. So these are all some of the things which it contains most of the things whatever I have discussed. Okay, with this, I would like to thank the Kreisel had asked us to do this complete exercise, which has been narrated and shared with you. I hope you did learn a few things through this lecture, and thanks for your kind attention.
Thank you very much, sir, for your excellent presentation. I should say it is a storehouse of information on ocean engineering. It is all about your knowledge, skill, attitude, what you have in this big topic, what is called as ocean engineering. In your talk, you have explained as how big can be an ocean wave, oscillatory motion with respect to crest and trough, challenges in extracting energy, site selection based on availability of wave power, classification of wave energy, conversion of the devices, and finally ocean acidification. Definitely, it is a rare opportunity for our students and also for the participants to listen to you, sir. And it is a very exemplary speech that we had for the past 1 hour, sir. Thank you very much for your presentation and for the talk what you have shared with your thought-provoking slides that you have used in your presentation, sir. Thank you, sir.
Any questions?
Participants, if you have any queries, you can ask.
Professor?
Yes. Can
Professor,
I stop? You want my presentation to be shared, or can I?
It's okay, sir. It's okay, sir. No, it's okay, sir. No problem. It's just a general question, sir.
Because I want to look at the audience also now. Okay.
Thank you very much, Professor. It was a wonderful talk. I worked with solar energy conversion.
Okay.
So, but when we compare this various kinds of renewable energy sources, ocean energy is one of the renewable energy sources, of course. But how far our country is focusing on this conversion?
No, ocean energy, definitely it's more complicated compared to solar energy because the technology is well known. But ocean energy, yes, we have been working from 90s, early 90s. No, in fact, early 80s we have been working. There are a lot of buts and ifs and buts. So now, see, globally, if you take, up to 2000 end, there was a strong research going on all over the globe. And suddenly from 2000 to end of 2010, it was a lull period. No one was interested in ocean energy. I don't know what is the reason. When I say ocean energy, in fact, to me, it's only wave energy, although you have other forms of energy. For our condition, wave energy should be, because it's easy to compile with other aspects, as I said. So I'm not biased towards wave energy, because tidal energy also is good. I have no, but then how do we then from 2000 to 2010, there was a lull period, no activity on wave energy. All of a sudden from 2010 or 2011, it has started. And now worldwide, there are a lot of work going on in wave energy. And that is, so even we were not doing any work between 2000 and 2010. And 2011, when I was in Norway, this project came up and we had a proposal. And then that's how it emerged. And now again we started. And I'm sure that this will take, and now we are more towards implementation. I hope something comes through.
Thank you, Professor. One more question. Most of the natural calamities like cyclone and low pressure regions, all these things are formed in the ocean region only. So when they are crossing from ocean area to land area, there will be a huge amount of the pressure created. So how this power plant can withstand the natural calamities in the ocean area?
No, we have to design for that. We have to design for that. So this is, one is the operational condition, another is the survival condition. We can take care of it. So operation condition, what I have presented is operational condition. That is how much of energy it can be extracted. Then the survival condition is how it has to survive the worst climate. So that also we have to take care, because you have so many bridges and other structures now, like that we can take care. Only thing, if it is a floating structure, we can just remove the anchors and bring it to the shore. But if it's a fixed structure, we have to design. We have to take care of it.
Thank you, Professor.
Professor, I have one question. Professor, I have one question. Yes. Can you hear me?
Please.
Yeah. I am Sukumar, Organizing Secretary of this event from Indian Chemical Society. So I have one question. See, instead of trying on the coasts, why don't you try this in the floating bodies like ships or submarines? Because they are already in water, they can use the energy better. And you can have more experimentation models also.
That is what NIOT was trying to do, that BBDB, which I also presented. It is a kind of a floating structure which can be fixed. So it can be, it is being tested by NIOT, because I don't want to put my nose into that. It's being tested.
Okay. Because there it can work better, because the floating bodies are already in water, you can have more models, you can develop more models.
One thing you should remember, the ship routes are such a way that it will take the energy where it is minimum. It will not go through where energy is high. So that is one big important point you have to have in mind.
Okay. But how about the ocean currents, they may be of some help to them,
Yeah. Ocean currents are deep. See, currents are varying over the water surface.
Oh, okay.
So ocean currents, as I said earlier, that maintenance of the equipments are not so easy.
Okay. Thank you, sir. Thank you very much.
This is Dr. Seshadri.
Yeah, please tell me.
I have a very exciting lecture you have, excellent. And I'm very happy that I learned quite a lot from you about ocean energy. Now, the last, as a chemist, you're talking about how is it possible to reduce the acidic concentration is possible. So one of the things which comes in my mind is we have a lot of sodium chloride in the ocean. If you are able to release the sodium plus into the ocean, somehow energy we're able to dissociate it into. The sodium plus will take care of the acidic. So the acidic, pH will definitely be becoming. This is my idea. But how it has to be done, I don't know. But another suggestion is, because sodium chloride is available plenty in the ocean, is it possible to dissociate some sort of mechanism by which you can, just like an electrolyte getting dissociated, Na plus and Cl minus. So the Na plus concentration will go up and the Cl minus concentration will come up. So in that way, it is possible to reduce the oxidation. This is my suggestion.
Yeah, maybe. I think because we have not taken up because there was an inquiry or interest shown by one of my old friend from the US, and in fact he is retired, so he is helping some other agency, and this problem came from them, and then we had only one discussion like this for 1 hour. So some went inside, some did not go inside. But now we have to take it up. In fact, I'm planning to look at the literature on this complete literature. I'll have to do a review of literature, and only after that we can think whether it will be worth taking up some work in this.
What I mean is, you can have a pilot plant in your own place, and then try to find out how much of sodium chloride concentration is there, how much of acidic concentration is there. Then try to take out the chlorine. I mean, sodium plus is a base that will definitely interacts with the acids, so it will become neutral. So to that extent, it is. I mean, I'm only telling you there is a possibility. I'm only telling how we are going to do it.
We will be roping in some of the chemical engineering department faculty and also chemistry department faculty later. But before that, I want to understand myself. So since the chemistry was coming into my title of this lecture, which I realized only yesterday night. And today, don't be when the question and answers for going on for the previous speaker, one day at that time I added those slides. Believe me or not.
Thank you, sir.
But in fact, I was a bit nervous whether there might be some questions from the floor, because there are all I see a number of chemist experts here. I understand. So I was a bit nervous, but luckily not much of questions on.
I am prepared to help if anything you want.
Please send me a mail. I'll be happy to be interacting with you. No problem.
Because I feel this is a major problem. The other one is, you're talking about the type of plant that you are having. You're able to do it only in Kerala. Is it possible similar plants can be done in other areas also? The coastal area.
Yes, it is possible to do in some other areas. In fact, we have identified some of the sites. We have identified 5 different sites based on different techniques. Those slides I did not present because I don't want to cover too much on thing. Already, I think I have given an overdose of I didn't want to cover. In fact, all those slides are there in my presentation, which I have hidden. If you are interested, you can just let me know. I can send an email to you. So we have identified and we have given to the CRISIL, the agency which is dealing with this.
The last question is, how much of Indian industries will be taking up your ocean energy concept into making it sort of viable projects?
Now I think it's taking a very big leap. I'm sure that things will move much at a higher pace. And there are a number of centers being organized here and there. Kerala, they have now recently there are a lot of administrative changes and institute changes also coming up. New things are opening up, and I'm sure that we see a very good scope and prospects for ocean engineering.
Last but not the least, we had tsunamis, in the recent times. To what extent the ocean energy level will change when you get tsunami?
Pardon me?
To what extent the ocean energy level, or whatever the level that you have, will it change or will it remain the same? Even to
tsunami is just a one-time thing, which lasts only for a short duration.
Okay.
And so it will not change any of the other characteristics of the ocean. No.
Thank you very much for all the excellent and
thank you. You are welcome.
I really appreciate you.
You're welcome. Welcome.
Good afternoon, sir. Very many thanks for your very beautiful lecture, sir. I would like to just ask, as a chemist, I would like to ask if the acidification of ocean, does it harm the power generation or does it alter the power generation, sir?
Power generation of what?
Through wave energy. See, you are
No,
trying to...
I don't think that is going to have any effect. That is not going to have any effect. That's a different issue altogether. It has more effect. People are talking about more on its effect on flora and fauna. Flora and fauna and environment. That is the only thing which we need to take care.
Okay, sir. Thank you, sir.
Thank you, sir.
Okay.
I thank our dignitaries for completing the technical session 2. Now I invite Dr. Ethirajan Sukumar, sir, Vice President ICS and Secretary of ICS Tamil Nadu branch, to brief the activities of ICS. Please, sir.
Thank you very much, madam. Actually, this program started well when we conceptualized everything 1 month back. But 48 hours ago, we had a shock from 2 proposed speakers that they were not available. And immediately, we could rope on Professor Sandeep as well as Professor Sundar. And really, we have to thank the speakers for their excellent presentation. And we got educated. We learned a lot from you too, sir. We are very thankful to you. So I have some slides. May I request Dr. Sivamurugan to project? So we are interested to explain the activities of the Indian Chemical Society Tamil Nadu branch. I would like to start with from the history of the Indian Chemical Society. Can I have the slides, please, Sivamurugan?
Yes, sir. I'm showing it, sir. Now.
Yeah, slide number 1. Start with 1, please. Yeah. Okay.
Are you able to see the full screen, sir?
Yeah. It's okay. Okay. Can I have the next slide, please? I would like to start with the history of the Indian Chemical Society. Actually, as Principal Madam and HOD Madam told, the society was started in 1924 when Acharya Prafula Chandra Ray returned to India and had interaction with like-minded peoples when the country was under British rule. And they had the model of Chemical Society of London. So they wanted to start one on the same model, and they started this Indian Chemical Society in 1924 with the University of Calcutta as the headquarters. Acharya Prafula Chandra Ray is considered to be the father of Indian chemistry. It was he who started the chemistry research in India and slowly propagated all over the country. Because during British rule, there were only teaching institutions, no research institution. It was he who started. Not only that, he started not only with the research institution, but also he started industry. Bengal Chemicals and Pharmaceuticals, still it is running very nicely. And during COVID, they actually prepared a lot of, manufactured a lot of medicines for COVID patients. So it's still going on well. So he actually connected academic, industry and research. So he started like that. His work was recognized all over the world, particularly in India. Even Mahatma Gandhi once told, if you say any person lived like him, a scientist like him, people don't believe, because he looks that simple and is a good teacher as well as a good academician and a good researcher. When he started, the society was having very limited people under the fold, and he started the journal also, Journal of Indian Chemical Society. And then, he started conducting annual events and biannual events. So slowly, the institution grew up, and now ICS conducts international, national, zonal, regional, and local activities throughout the year. So after this digital invention has come, now it is going all over the world. What are the programs we are conducting is going all over the world through the website, through the internet. So every year, normally, every year annual convention used to be held in different parts of India, and many scientists, professors used to take part. Even they used to invite Nobel laureates to give lectures. So actually, the journal, particularly which is in the 90th year of publication, now last year it has been handed over to Elsevier. Elsevier is doing very good job. Now, the important pillars of this Indian Chemical Society. May I have the next slide, please? Yeah, the present president is Padma Shri Professor Ganpati Yadav, G.D. Yadav, former Vice Chancellor of Institute of Chemical Technology, deemed university in Mumbai. He enjoys lots of support from industry. So he took charge in January 2020, and now he has brought in a lot of money from the industry to the society. So with that money only, now everything is digitalized. All the back issues of the Indian Chemical Society is being digitalized, and now the journal has been handed over to an international publisher. Now the impact factor is going up. lots of papers are being accepted from abroad, and we request you to submit your papers to the journal also. So another important person running the affairs of the Indian Chemical Society. Of course, there are many. I'm pointing out only two for want of time. Professor Chittaranjan Sinha, former HOD and present professor of chemistry in Jadavpur University. Very dynamic secretary we have, and he has been doing very good job. Actually, he is going to every institution in and around West Bengal, even to other states. Even visited Chennai year before last to give a keynote address in one of our symposia. Next one, please. Next one. So the Tamil Nadu branch, actually, in it was started in 1970 as in Madras branch by Professor Shantappa, former Vice Chancellor of Madras University, and it was the director of CLRI, Central Leather Institute, and Professor Swaminathan, head of Department of Organic Chemistry, and NS Janaprakash from Laila College, and Professor Shanmunathan from Pachaipas, and Professor Venkatesubramaniam from Vivekananda College. And many professors joined, and then they started. It had a very humble beginning, and then they conducted the 19th Annual Convention of Chemists jointly with IIT Madras and University of Madras in 1981. And every year, Professor Jnanaprakasam used to organize annual symposium on particularly on annual symposium on chemistry on August 15th. So many eminent chemists used to come there and give talk. So in 2001, we have taken over the institution because after the retirement, there was a lull period. Then we have taken over and we renamed as Tamil Nadu branch, and it started functioning from the new college with the principal of new college as a president and other office bearers from other colleges. Then we organized workshops on water analysis, invited lecture from scientists from DuPont and senior professor from Calcutta, and we organized a one-day symposium chemistry and environment. So after that, the branch underwent a lot of changes. Now a team of youngsters are guided by the seniors has taken over. And since 4 or 5 years, we organized lots of events, and the important among them are the one-day symposium on chemistry biology interface Laila College, and chemistry and industry in New College, and 2 invited lectures by Professor Kuppuswamy, former student of Pachaipas College chemistry, and now he's a very senior professor in Dartmouth Medical School, and he actually gave 2 invited lectures in Stella Maris College and Sri Ramchandra deemed university. In collaboration with the Royal Society of Chemistry Southern India chapter, we organized those events. And from July, we organized so far, this is the 4th event, 4th webinar. The earlier ones were in collaboration with the Pachaipas College, Madras Christian College, and Kandaswamy Naidu College. This is the 4th one. May I have next slide, please? So these are all the office bearers of the Tamil Nadu branch of the Indian Chemical Society. Dr. Seshadri, actually is alumni of Delhi University. He worked with senior professor, Professor T.R. Seshadri, a legendary figure in chemistry in those days in 60s and 70s. Then Dr. Venkatesh is the HOD of chemistry in Pachaipas College, Madras. Then myself, secretary. I was the Dean of Research in Savitha deemed University. Then Shivamurugan, Joint Secretary, is Assistant Professor of Chemistry in Pachaipas College. Then Dr. Khalilur Rahman is Associate Professor of Chemistry in the New College. Then Dr. Balakrishna, a former scientist and presently emeritus scientist in Entomology Institute of Laila College, and is one of the EC members. And Dr. Mary Judge Madam, she is Associate Professor in Stella Maris College. Then Dr. Karthikeyan is Assistant Professor in Dr. Ambedkar Government Arts College. Then Dr. Rajkumar, Assistant Professor from Madras Christian College. Then Dr. Ian Pillai, he is from Assistant Professor from Pachaipas College, Chennai. Then Dr. Kalimuthu is Assistant Professor from Gandhigram Rural Institute, Dindigul. Then Dr. Akilandeshwari, the Organizing Secretary and the main source of inspiration and model for us in organizing these kinds of program. She is also Assistant Professor in Sri Sharda College for Women. Then Dr. Hariharan, who organized the previous webinar, is Assistant Professor and HOD of Chemistry in Sri Kandaswamy Naidu College. So these are the active people who are guiding us actually and working throughout the year to make things fruitful. May I have the next slide, please? Yeah. So future plans. So for want of time, I want to shorten the presentation. So in future plans, we have lots of plans for particularly for young students to come up in their life, in their own field. So we are having lots of, we are planning to organize programs for the benefit of students right from school, and UG and PG students and research scholars and faculty members. And we are planning to organize a symposium and hands-on workshop on specialized techniques like HPLC, phytochemical methods, or nanotechnology, like that. We have lots of, now science has grown. Now chemistry has entered in many fields. No, when we started learning chemistry in 60s and 70s, it was confined only to certain areas. Now it has gone to different areas: physics, chemistry, biology. Everywhere now chemistry is there. Now the present generation should learn those things, and we want to be a bridge between the one end and the students. Okay, and we are even planning to organize tours. So actually, a tour to industries and national laboratories, because the exposure is very, very important. As far as India is concerned, particularly the southern part, the students are not that much exposed to these kinds of things. So the visit to national laboratories, interaction with the scientists will help them to actually enhance their potential, enhance their knowledge and their talents. So, and assistance in internship programs. See, many industries are asking for some people, some students intern. When we ask some students, they are not interested to go because they are very choosy sometimes. So we want to have these things in advance so that we can pick up the students and keep ready. When industries want, we can send them. So like the training programs for faculties on emerging areas of research in chemical sciences. Because we feel the teaching faculties need periodical updation. In medical field it is there, CME, they organize CME, continuing medical education program. Pharmacy institutions have continuing pharmacy education program. Even nursing people have continuing nursing education. But in chemistry, we lack this one. So on behalf of Indian chemistry, we want, Indian Chemical Society, we want to take this area and we want to update. So particularly, instead of all teachers coming to one place, we will go to some places, designated places in different parts of the state, and ask the teachers from different colleges and adjoining districts to come and assemble there. We can update and we can invite experts and then ask them to upgrade their knowledge, because now everywhere, funding is very essential for teaching staff. They have to apply for funds and get grants or go do research, publish papers. So this is possible only by these kind of interactions. And organizing programs in various parts in Tamil Nadu in association with the local institution. So we request the participants to be in touch with your HOD or principal. Please ask them to take help from us. We are ready to visit your place and then organize such programs in collaboration, so that your institution will get upgradation. Okay, your institution will get exposure to the all India level. So now we are collaborating with the national institute, national body, professional body, and which is internationally known. As Principal Madam told, in another 2 years we are going to celebrate the centenary of Indian Chemical Society. And we are also interested to form experts pool, because sometimes some companies ask us whether we can solve some problem. Like Professor Sundar told, many companies approach us when we do some good work and show our talents. They come and ask for solutions to some of their problems. So we are interested to form experts pool, so that we can address the current situation, current interest, current crisis. So if, for example, during the flood we have some crisis, during this pandemic we had some crisis, and during this pollution. See, for example, pollution in Delhi, the environmental pollution. I think only chemists can solve these problems very easily. Okay, but we need a proper forum, proper group of experts, so that we can, the governments or organizations NGOs can come to us and we can lend a helping hand. We are interested in starting the student chapters. Particularly our president and the secretary, honorary secretary of the Indian Chemical Society, they are very particular about student chapters, and we have opened up student membership. If a first year student in the BSc, if the student pays 500 rupees, becomes student member, he or she can continue for 3 years till the student finishes the degree. And if she is continuing PG till it is continued. So once they finish the degree, they can become life fellows by giving the difference of amount, and they become life members. Because this actually insists, we are trying to inculcate the professionalism in the minds of young people. Because we traveled to different countries and we worked in different parts of our country. So we see we lack professionalism in our field. So this should be inculcated in the minds of youngsters. Present day academia, the teachers cannot do this because they have tight program. They have to do lots of jobs other than teaching. So whereas organizations like us, professional bodies like us, we can take over, we can come to your help. So it's up to you to make use of our services. And we are requesting you, those who are attending this webinar, those who are not members, we want to enroll more members, fellows, members and student members. Please try to become members. Next slide, please. You can go to our website, Indian Chemical Society website, and then online, you can do the payment also by online. You can fill up the form online and then send to this one. So that by joining the professional body, you are also elevating yourself. You are upgrading yourself. This is very, very important. So when you go up, it gives self-confidence. It gives you exposure to people. So when you go for a job, you can face the interview very boldly. When you work in a company, when you go to a company and work, or in industry or a government institution, when you face problems, this kind of context will help you to solve the problem. So these kinds of things we want to inculcate in the minds of youngsters. And we also request you to patronize the Journal of Indian Chemical Society by subscribing. Please go to the website and then do the needful. And then we have planned to organize programs in your institution also, as I told you. So the Tamil Nadu branch will help you. Please be in touch with us. So our branch contact is Dr. Shiv Murugan. He is a joint secretary and a vibrant member of our team, and is working as the Western professor and is in the PG and research department of chemistry in Pachipas College, and we are given his email ID also. So please help us to do better work, and then we want to reach to different people. So actually we want to next meeting in the executive council meeting, we want to inform our members we are going to fix targets. So we are going to enroll more members. We want to reach to different institutions. We are contacting many people over phone and email. Please, you also can do it. So as a member or a well-wisher of the Indian Chemical Society. So thank you very much for sparing your time to listen to me. And thank you very much for the organizers. And I thank Sharda College for Women to come forward to organize, hold this as one of the hosts. Thank you very much.
Thank you, sir.
Thank you, sir.
Now I request Dr. Seshadri sir, Chairman, ICS Tamil Nadu branch, to give the concluding remarks for this webinar. Please, sir.
Thank you very much, all of you. First of all, are you able to listen? You're able to hear me? Okay?
Yes, sir. Yes, sir. Yes, sir.
Yeah. It is a very enlightening session we had right now. It is mainly because of our secretary and Sir Murugan, and everybody was able to do it. Of course, nonetheless, your continued interest in finding out how these things can go through. And of course, the two topics are excellent, important topics which are going to be there. And definitely, as I was telling, initially we had some sort of anxiety, but that has been solved by two eminent people in this field, and they have done given a wonderful presentation, and it's really a learning process. So I'll just, it is very difficult to summarize everything, but a few points that they have given, that will be an additional information for all of you, especially for students who are just later joined here. Now, first we had a lecture from Dr. Sandeep Mavaria. He is, LANL. He was able to discuss about lab involving nuclear energy, climate energy. Of course, the topics he was covering was material for further science signatures and complex, etc. His main work is working on fuel cell program. This is a fuel cell program. It's a very important, milestone in the history in this field. He was talking about primary polymer electrolyte membrane, what we call DOE, ERE, FCTO fuel cell. Then fuel cells transportation system. Then he had supercapacitors, it's very important. And then he was talking about how hydrogen plays an important role. As a chemist, we are really excited about this, especially conceptual hydrogen, scale energy system, hydrogen for transport, synthetic fuel, and then electronic grid infrastructure, and then renewable for production of hydrogen, especially even it goes into nuclear energy. And then we have hydrogen oxidation, LAN, enabling oxygen reduction, breakthrough thin films, then proton exchange, membrane fuel cell, and of course, anion exchange, because whenever you talk about hydrogen, we expect an anion exchange. And then we have carbon dioxide reduction reaction, CO2 PR and CO format, and going into ethane, etc. And then we have even ASAP. This can even go into the food coverage area, redox flow matrices, all vanadium. And he was concentrating about the two important catalysts, platinum and also vanadium contract. And we have, what are the things which we are going to have? Lithium, effect of phenyl absorption in alkaline membrane, especially safe form cells, alkaline membrane fuel cells. And then he was also depicting it, how it has been done through polarization curves. He was able to explain to us how it works, this fuel energy. And then we have got sluggish HOR in alkaline solution, hydrogen oxidation reaction. We have the platinum ruthenium catalyst in AAMFCS, platinum ruthenium. Intrinsic activities of these two catalysts, PTC and ruthenium catalyst, HOR mammograms. These are all very important because these are all things we were never heard of before. It is going to be a knowledge enriching topic in benzyl ammonium, absorption energy of BTMA, and then microelectrode cell test using thin film monomers, comparisons of poly and Co2FC. Then we have phenyl absorption impact, PAMFCS, and also impact of polymer backbone phenyl grouping. Is as Dr. Sivamurugan was also asking about it. This goes into the very vast, very important area of polymer, AMFC performance, and then we have AMFC study on platinum and the ruthenium, optimize the AM performance, and then what is the result? Then we got RDE micro, MEMC can compare with the stage that phenyl suppression POP2, he talking about iron, tris intermediate complexes, nonaqueous redox battery, what we call NARFPS. Then we have got iron complexes basic based on NARFP, and then we have got synthesis of this compound, iron to methyl pyrimidine triplates, and bulk electrolysis. They're very important because normally you have the electrolysis play important role in electrochemistry. Then he was discussing so much about bulk electrolysis. And then what is the result? The result is there is a possibility of synthetic pathway, and then this complex of a methyl porphyrin complex will play an important role. This is just a briefly covered about this. This is the first lecture given, the scientist given by this. And later, the second was excellent by Professor Sundar, who is a professor in IIT and professor of head of department, and also the professor. And of course, as when he was reading about his biodata CV, it was something amazing, and it was so happy that he is able to share some of his valuable ideas to our lectures. And he was talking about major operation tides, wave energy mainly, tidal and wave polar development in India, how it is being developed, status of existing tidal and wave projects. Now, tidal project, wave power, we call it a PBDFP, assessment of tidal power potential India, how is it working? Then total levels, along with the base time, and then we have got present approaches, estimation of wave power, wave stimulation, wave energy concentration. The most important thing is that he was able to estimate to the current generation of 41,000 megawatts. This is a very important because nowadays we are having a lot of power shortage, a lot of things which are going through because, alternately we are not getting electricity in our houses. This will play a very important role. And then he was talking about availability of the local demand, what we call SIT election selection strategy, erosion residue, and wind downfall, dominated field, and also they got energy conversion. And also he was talking about how there are some energy losses in this field, about air and other things. Then he was focusing mainly on giving us a brief history of wave energy, and then surface oscillation, relative buoyancy. And then he was talking about how this wave energy we can classify, because we know there is an energy, but is it possible to, yes, there's a possibility, terminator, attenuator, then point absorbers we call, and then attenuators, e.g. Then we have near shore bottom, floating bottom, standing, overlapping oscillation water columns, and what are the advantages? Demonstration, and there's a demonstration plant that he was explaining to us in Kerala how this wave energy can be done. Then what do you call mutic functional, the different concepts we have, mainly OWC combined with breakwaters, water flume, coastal protection measures, he was talking about it, and then experimental run. He was able to have an experimental run on this. Ocean acidification, he was talking about some American scientists or comporting it, how the acidification, how the acidity of the pH or the acidity of the ocean can be reduced because the concentration can be reduced. Then this is it is more acidic. So in that way, starting from energy, electrochemical energy, we went to a broad range of ocean energy. This is a central experiment, and I'm sure most of the people who are listening to this, and you can even contact them if you want, and there is an email and everything available. Definitely, Professor Sundar sir, we are interested to collaborate with you in IIT. If it is possible for a small workshop, or any of the present college can have, or different colleges in meeting, it will be very useful for the students because learning is always a process, never ending. And I'm sure that it is a guiding post, both of them as the guiding post, all of us. And I'm sure this is going to be an eye opener in our, in fact, in our ICS also, as Dr. Kumar is telling, we are keen on teaching some of the major concepts of science to different colleges, mainly because the reason is the young minds alone can give us how type of it can be, be experimented, and they can definitely give us more ideas, young students, and definitely we have been organizing more than 2-3 colleges. The reception is very good, and I'm sure we will be conducting more, as Dr. Kumar is telling, akin to different colleges. Well, definitely we can. So in that way, ICS is playing a very important role in popularizing the basic concepts of science and the research involved in this by eminent scientists. Most of the time we are having eminent scientist people because these are the people who, as I was telling Dr. Kumar, we know only by name. Now we are able to see them. Thank you very much for the presence. And I should thank also for the Sarda College, Madam Agilan Desri, for an excellent arrangement she has made. And I'm sure in the future also, we will be able to have such lectures. So we simply thank the college people, all of them, including everybody, for having collaborated with ICS. Ma'am, sure, we'll be able to help you at any time. Thank you very much. That's all.
Thank you, sir. Now I request Dr. K. Bharati Madam, Assistant Professor of Chemistry of our college, to present the event report. Please, ma'am.
Good morning to one and all. With the blessings of God Almighty and our revered Ambas, we, PG and Research Department of Chemistry and Indian Chemical Society, has jointly organized an international webinar on sustainable energy and green chemistry today. The event started with prayer song. Dr. S. Sankari, HOD of Chemistry, welcomed the gathering. She also welcomed the resource persons and appreciated the efforts taken by Indian Chemical Society to popularize the ICS among the staff and students. Our esteemed Madam Principal has delivered the presidential address. She highlighted the significance of the sustainable energy, which is the need of the hour. She also expressed her appreciation to the ICS team for their efforts to make this webinar a grand success. The first technical session was chaired by Dr. S. Ayyam-Pillai, EC member, Indian Chemical Society, Tamil Nadu branch. Resource person, Dr. Sandeep Maurya, scientist, Los Alamos Laboratory, New Mexico, USA, enlightened the audience on electrochemistry for the sustainable energy future. He touched every aspect of electrochemistry, such as batteries, superconductors, hydrogen fuel cells, which are the future energy providers. His presentation was extremely illuminating, useful, and enriching. The second session is chaired by Dr. S. Geeta. Professor Vallam Sundar, Emeritus Professor, Department of Ocean Engineering, IIT Madras, gave a wonderful presentation on energy from ocean and green energy. He enlightened us on renewable energy sources such as wave and tidal power plants, energy conversions, and their operational conditions. His presentation made a very enriching and eloquent deliberation on the topic was very much motivating and highly informative. Next, Dr. E. Sugumar, National Vice President, Indian Chemical Society and Secretary, Tamil Nadu branch, has briefed about the activities of ICS. Dr. V. Seshatri, Chairman, Indian Chemical Society, Tamil Nadu branch, has presented the concluding remarks about the webinar. Dr. Kalpana, Assistant Professor of Chemistry, compared this international webinar. Around 160 participants comprising a blend of professors, research scholars, students. Out of this, 152 participants within India and 8 participants outside the country from South Korea and Thailand attended this international webinar. With these few words, I would like to thank for giving this opportunity. Thank you.
Madam, with the permission of Akhilandeshwari, Madam, can I invite our Honorary Secretary who is on the line? Can I ask him to talk a few words?
Sir, it's our pleasure, sir. It's our pleasure.
Okay. Sir, Sinha sir, Professor Sinha, can you say a few words?
Yes, sir. Yes, sir. Thank you,
please,
sir.
Please come on the line, sir. Come on the line.
Are you hearing me?
Yes, sir.
Hello. Hello, can I hear you, sir?
Yes, sir. We can
Yes,
hear
sir.
you.
Yes, sir. Yes, sir.
Okay. Thank you, sir. Thank you. Very nice program you are organizing, sir. And already everything Professor Sukumar has demonstrated about the chemical society and its planning, etc. And in fact, you are organizing, particularly under the leadership of Professor Sukumar in Chennai, a nice activity, branch activity, students activity. Because of this pandemic situation, we are not going through our offline program, but certainly we will do it very shortly. And besides, you please go through our website, and journal is now maintained by Elsevier. So its impact is gradually increasing. And besides that, we are going to publish one education journal. And already its periodicals is publishing, but we have applied for ISS and then we'll go for the education journal for Indian Chemical Society. Along with Chemical Barta, the activities of Indian Chemical Society in quarterly, we are uploading in the website in the name of Chemical Barta. So you can, if you visit our website, just to write Indian Chemical Society in Google, then you can easily enter. Or you can write www.indianchemicalsociety.com, where you can find our previous journals also. All our previous journals since 1924, since it started in 1924 to today, every copy will be available freely in our website. Very soon will be coming. Some of the issues already uploaded. So every paper you can go through it. And it certainly will help our readers as well as the researchers very much. Since the time immemorial, you can recollect it. In the publications of Priyadaranjan Rai, one of the pioneer worker in the field of coordination chemistry of silver 3, copper 3, and many other compounds. Besides the work of P.V. Sarkar, a giant of analytical chemist, or work of B.C. Guho and Professor Seshadri, and also different other professors from different European countries, their publications will also be available. But this is one important part for the researcher. And every year we are organizing at least 4 programs and 3 programs for students from school and college age. They are going for the different competitions. Through that competition, we are selecting very quality students. That is, our objective is to improve the quality chemistry, and from which the good publications will be coming, and in future the country will move faster. And as you know, in terms of publications, our country is the 3rd largest in the world. From the Scopus viewpoint, it is the 5th one, or from the NSS, National Sample Survey that shows you the third best in the world. So whatever may be, large number of students, more than 3 crores students are learning chemistry, and Chemical Society is going to reach with them. And you are the torchbearer of it, and Professor Sukumar and other people, Sivamurugan and many other people. And I do invite all of you to join with us. The people, scientists or the chemist, or you can physicists and biologists, those have chemistry in their undergraduate courses, all they can be the member of the society. If you get membership or the fellowship of the society, you can enjoy 5 years free subscription of the journal. Free subscription of the journal for 5 years with 3,000 rupees. This is one of the great achievement of Indian Chemical Society. And I think many of you are either already member or many of you are going to be member. Besides the students chapter, that is the idea of our present president, Professor Jadhav, that the initiation of students chapter in your colleges, only students can pay 500 rupees for each full period of studentship. As long as he remains student, at least up to a master's course. After master's course, suddenly we should not consider he or she as a student. He will be researcher or like that. Up to master's course, a student who enlisted as a member with 500 rupees, he can enjoy all sorts of chemical activities in our society. So in the December 21st to 24th, and our 58th annual convention will be going to be held in a virtual mode. And there are 9 different sections. Out of these 9 sections, the most important one, interesting one.
Excuse me, sir. Sir, your mic is mute, sir.
I think it is now okay.
Yes, sir.
And another program that is that it is being organized by the Hyderabad University under the banner of Indian Chemical Society during the same time. This is the Young Scientist Conclave. Professor Ramachari, he is the convener of this program. And besides, we have organic, inorganic, analytical, applied and industrial, and environment, and so on. So 7 other sections in 7 different places of the country. See, this Women Scientist program is being organized by JNU Chemistry, Jawaharlal Nehru University. And the organic chemistry is being organized by IIT Kharagpur. And inorganic chemistry by University College of Science, Kolkata. And then physical chemistry is being organized by our physical chemistry, perhaps it is in Bombay. So different places, along with the different corporate sectors like ONGC, IOCL is organizing this applied and industrial sector. So different places they are be organizing. So I do request to be registered for the for 4 days. Day 1, 21st to 24, you will participate in any section. So please. So you are organizing very nice program. I heard Professor Sundar's lecture, very nice, and it is encouraging. And today, the environmental disaster, and within 2050, it is reported that within 2050, Kolkata, Bombay, and Visakhapatnam, these 3 important port area will be flooded. So that is very important notice to us. So thank you, Professor Sukumar, for giving this chance to me also to meet with the friends joining with the program. Thank you, sir. Thank you.
Thank you, sir. Expressing gratitude and appreciation with extra enthusiasm can emphasize the extent of our thanksgiving. I request Dr. L. Akhilandeshwari, Assistant Professor of Chemistry of our college, to propose a vote of thanks. Akhila.
Thank you, Dr. Kalpana. Life is a precious gift and gratitude is the greatest wealth. So goes the saying of a great humanitarian. I am here to express my gratitude through proposing the vote of thanks for the entire deliberation today. Words won't suffice to express the thankfulness to the Almighty that showers His grace on all of us, and indeed, He made this whole webinar fruitful. My profuse gratitude is due to our esteemed Director Amba and esteemed Secretary Amba, who not only facilitate our accomplishments, but also fill our path with their generous blessings. I'm indebted to thank our vibrant and meticulous Madam Principal, Dr. R. Umarani, who encourages us towards more and more productive work. And I also thank her for graciously presiding over today's session with her insightful thoughts. Thank you, Madam. I also thank the controllers of examinations, Dr. E. Roja and Dr. S. Geeta, for their continual support. Now, with a profound sense of gratefulness, I thank both the resource persons, elite scientists, veterans, Dr. V. Sundar, Emeritus Professor, Department of Ocean Engineering, IIT Madras, and Dr. Sandeep Maurya, scientist, Los Alamos Laboratory, for their very, very informative talks in both the sessions. Both of them gave very, very important informations and advancements in the field of ocean science and harnessing of tidal energy and the techniques involved. The fuel cells research, which is a very, very important in today's scenario, when all of us are looking for alternatives and supplements for energy. Also, the ocean acidification problem is a problem that Sir has thrown to us chemists audience, so that we may get stimulated towards our with our research temper. I now thank Dr. I.M. Pillai, EC member, for chairing the session 1, and Dr. S. Geeta for chairing the session 2. I thank Dr. E. Sukumar, the Secretary, ICS Tamil Nadu branch and Vice President ICS, for being a pivot, monitoring all the activities, suggesting us in each and every step. His mentoring is really amazing. I also thank Sukumar sir for throwing light on the activities of Indian Chemical Society and inspiring all of us and our students too. I thank the chairman, ICS Tamil Nadu branch, Dr. V. Sheshadri, for his benign guidance for the conduct of today's program and for sharing his concluding remarks for today's deliberations. I will be failing in my duty if I don't mention the pillar-like support rendered by Dr. V. Shivamurugan, Joint Secretary, ICS Tamil Nadu branch, who not only introduced 7 of us of Department of Chemistry, Sri Sharda College Government to Indian Chemical Society, but he kept on supporting us in all aspects for the excellent conduct of today's webinar. I now thank all the dignitaries of Indian Chemical Society for participating in this webinar and supporting us. And I am profusely thankful to Dr. Chitranjan Sinha, Indian Chemical Society Honorary Secretary, who had joined and given a short note on ICS in this session. And we promise to take part in the annual convention, sir. I now register my deep sense of gratitude to Dr. S.A. Sannasiraj, Professor, Department of Ocean Engineering, IIT Madras, and Dr. Ramayan Kannan, Research Associate Professor, University of Mexico, who were the scheduled speakers of today's webinar, and due to their unavoidable preoccupations, graciously introduced us to the very eminent experts of today's session. I place my profuse thanks to both of them. Now it's my turn to thank our HOD Madam, Dr. S. Shankari, Associate Professor of Chemistry, convener of this program, for steering us throughout the events, following each and every step and taking care for the perfect conduct of the program. I also thank her for delivering the welcome address. I also thank the co-convener, Dr. K. Bharati, Associate Professor of Chemistry, for presenting the events report, and the whole organizing committee, Dr. A. Kalpana, Assistant Professor of Chemistry, who facilitated the whole session through her beautiful coordination, and Dr. S. Anbuchelvi, Dr. V. Janaki, Dr. K. Revati, and Dr. R. Kavita for their wonderful support in this event, as ever, without which nothing could have been possible. I'm very much thankful to all the participants, learned professors, and students who made this webinar a great event and for keeping the session more productive through their valuable questions. Once again, thank you, one and all.
Thank you, Akila. We once again thank the resource persons, the dignitaries of ICS, professors of our college and other college, and all the students for taking part in this grand event and making it a success. Thank you. Hope you all will cherish this good experience of our webinar and our combo with Indian Chemical Society. Let us conclude this program with our college song. Darshini.
Shanti Nilayamam Sharada Devi Jaya Jagadishwari Om Jagadishwari Jaya 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 Jagadishwari Om Jaya Shanti Nilayamam Sharada Devi Jaya Jagadishwari Om Jagadishwari Jaya 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 Jagadishwari Om Jaya Shanti Nilayamam Sharada Devi Jaya Jagadishwari Om Jagadishwari Jaya 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 Jagadishwari Om Jaya Shanti Nilayamam Sharada Devi Jaya Jagadishwari Om Jagadishwari Jaya 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 Jagadishwari Om Jaya Shanti Nilayamam Sharada Devi.
Thank you. Akila, shall we?
Huge thanks to one and all. Heartful thanks to all.
Thank you. Thank you, madam. Thank you very much.
Thank you so much.
You made it possible. See, Sharda College has already, already is known for quality. Okay. you keep your flag flying. Good. Very good. So I'm very happy Professor Sinha has participated. Without our request, just he just came on the line, and I'm very happy. So thank you, Sinha sir, for your participation. Okay. Thank you, ma'am. Thank you all. Thank you very much. We'll be in touch. Stay in touch. We should not stop with this program. We have to go further. Okay. This is the first level. We have to go to next level. Okay. We will be interacting with you. Thank you very much. Thank you,
sir.
Thank you.
Thank you, madam.
Thank you, sir. Thank you.
Sir.
Thank you, Sivamurugan sir.
Thank you, sir.
Thank you, one and all. As chairman of this, I'm very happy that it has happened. And I'm sure this is the only catalyst. Grow more. And as I was telling Dr. Kumar, more and more such lectures should be organized. I'm very enthusiastic about I'm very happy about the enthusiasm shown by your college people and also yours, and ably participated, all these people. Thank you, one and all, on behalf of this. Thank you.
Thank you.
Thank you, sir.
Thank you so much. Sir, shall we close, sir?
Yeah, we can close it. We can, okay. We can close the program.
Shankari ma'am, I'm closing. Sir Sukumar sir, I'm closing, sir. Shivamurugan sir.
Go ahead, madam. Go ahead.
Yes.
Thank you.
Please go ahead.
Thank you, sir. Thank you so much.